This lecture is about periodic trends, and just as a reminder, the periodic table was originally set up so that elements in the same group or families have similar properties. And so we're going to talk about some of the properties that repeat as you reach the similar level on each period of the periodic table. The primary reason that elements in the same group or family have similar properties is because they have the same number of valence electrons, or electrons in their outermost or highest energy level shell. And it is these valence electrons that undergo chemical reactions, and so that's really what determines primarily the reactivity of elements. There are several properties that repeat on a periodic basis as you move down a family or group. Atomic radius, or the same type of trend for ionic radii, ionization energy, electronegativity, / I'm going to add here electron affinity, and reactivity and metallic character. We won't really talk about all of them, but I just wanted you to kind of see that there are a large number of properties that elements in the same family share properties with. So just a couple slides to discuss the concept or a little bit of theory behind some of the properties that elements share. And I think the most important basis for these properties are Coulomb's law, which is a formula that explains the attraction or repulsion charged particles have with each other. So as I'm sure you know, if you have two particles that have similar charges, let's say they both have a negative charge, they're going to repel each other. And the larger the value of the charge, the stronger the repelling energy or force is. If two particles have opposite charges, plus and minus, for example, it's going to be an attractive force. And again, the larger the value of these charges get, the stronger the energy of attraction is. Also, so this last bullet is the important one. Also, I've explained how the charge in the particle is directly related to the energy of attraction or repulsion. Look at the denominator here. This is the distance between the particles. So I think that's kind of intuitive that as particles get closer together, that means as R gets smaller, then the energy of attraction gets larger. Okay? And the farther apart the particles are, in other words, the larger R gets, the smaller the energy of attraction. Apologize to my dog. She's trying to play fetch. All right, so what are the particles we're talking about? Well, the charged subatomic particles in an atom. So electrons, of course, are negatively charged, so they're going to repel each other. All the electrons in an atom repel each other. So if you think about the Bohr's model, where you have the nucleus of an atom and then you have the energy levels that the electrons can exist in, the valence electrons that are in the highest energy shell, experience what we call shielding due to electron-electron repulsion of these inner electrons. So this electron out here is feeling an attraction to the nucleus because the nucleus is positively charged, the electron is negatively charged, but these other electrons in the inner energy levels are essentially getting in the way, so that this electron doesn't feel the full attraction of the nucleus. That effect is called shielding. Okay, so that'll be important to remember to explain some of the periodic trends. So the net attractive effect an electron feels with the nucleus is called the effective nuclear charge, ZEF for short. So let's say that let's think about the carbon nucleus, okay? So you have 6 protons in the carbon nucleus, and let's talk about some of the electrons out here in the highest energy level. This electron is not going to feel the full force of 6 protons in the nucleus because of the inner core electrons. But the attraction it does feel will be referred to as Zeph, but that will be less than 6. All right, so all periodic trends. So we're going to go over primarily 3 or 4 different types of periodic properties. All of them can be explained either by using effective nuclear charge, Zeph, or by using the phenomenon of shielding, where the inner core electrons interfere with the force of attraction. And so you will be asked to explain what a trend is it increasing or decreasing, and then explain why it is that way. So Zeph, that is the effective nuclear charge between electrons and protons, increases going left to right across the period. Okay? And so if you envision the periodic table, okay, so we got hydrogen here, helium here, and lithium, etc. Okay, as you move left to right across any period in the periodic table, effective nuclear charge is going to increase. And that's because with every step in the periodic table, you are adding protons. Okay, so the electrons in the outer shell are feeling a stronger and stronger pull to the nucleus. So effective nuclear charge increases going from left to right. Effective nuclear charge decreases going from top to bottom, and that's simply because with every step down the periodic table, you're adding an energy level, okay? And so the electrons are getting farther and farther and farther away from the nucleus. And as they do get farther and farther away, they obviously feel less attraction to the nucleus. So that is why Zeph, or effective nuclear charge, decreases going down a group. So here is a typical multiple choice type question, similar to one that you might see on an exam. It's asking you which element experiences the stronger effective nuclear charge, magnesium, aluminum, or sulfur. And so you would have to refer to a periodic table, unless you have them all memorized. All of these happen to be in period 3 on the periodic table, and magnesium is in group 2A, aluminum is in group 3A, and sulfur is in group 6A. So then you have to remember the trend for effective nuclear charge. Going left to right across any period, effective nuclear charge is increasing. So that means that sulfur would experience, the electrons in sulfur would experience the greatest effective nuclear charge. And remember why that is. Simply sulfur has more protons in its nucleus. Therefore, you can think of it as creating a greater magnetic attraction to the electrons. And magnesium has the fewest protons, so the least strong effective nuclear charge of its electrons. So magnesium's the smallest, sulfur's the greatest, so the correct answer would be C. All right, now we're going to talk about some specific periodic trends. We'll start with atomic radius, and just think of size. When you are discussing atomic radius, just think of the size, which is defined for an atom as the radius is the distance between the nucleus to the outermost valence electrons, okay? So that's the radius we're talking about. Look at any period at what happens to the size of the elements in that period. All right, and then look down a group and look what happens to the size. see if you can think of any reason why, explanation that you could use, why these trends exist as they do. And then we'll discuss that in the next slide. So hopefully you noticed as you go down a group, the atomic radius increases. The atoms get larger and larger. That is primarily because you are adding an energy level with every step down the periodic table, and every energy level gets farther away from the nucleus. Okay, so the atom gets larger and larger. As you move left to right across a period, this is counterintuitive, so I think you should make a note of this. I would jot this down, highlight it, some way to remember, because it's against what you might think. So as you move left to right across any period, the size of the atom actually decreases. They get smaller. And a lot of students think, wait a minute, we're adding subatomic particles. We're adding neutrons, protons, electrons. How on earth is it getting smaller? So do you remember a couple slides ago I said you can explain every periodic trend either with shielding or ZEF, effective nuclear charge? Well, any trend, any of the trends we talk about from left to right can be explained with effective nuclear charge. So just that's another good thing to write down. In this case, atomic radius or size, remember effective nuclear charge increases going left to right across the period. In other words, the electrons are getting more strongly attracted as we add protons. And what happens to the size? What happens to anything when you get more strongly attracted to it? You move closer to it. Same thing with the electrons. They're feeling more and more attraction to the nucleus because we're adding protons. Therefore, they try to get closer to the nucleus, and that makes the overall size of the atom shrink. And so I'm not sure this is going to work on my iPad. It's a dynamic movement thing. I don't think it's going to. No, there's no way to get it to work. This will be cool. You'll see it in my live lecture, though. If you click on this slide, what happens is, first of all, let me point out that sodium and magnesium are both in period 3 of the periodic table, and magnesium is farther to the right, so it should be smaller, right? And so what happens here is, this is a dynamic video, so that it shows the magnesium atom shrinking. So to explain the trend in atomic radius a little bit better, look that sodium has 11 protons and magnesium has 12. So the electrons in magnesium are a bit more strongly attracted to the nucleus because there are simply more opposite charges. And so because of that, the size of the magnesium atom actually pulls in tighter and it ends up being smaller. Down a group's a little bit more simple to understand. This is comparing lithium to sodium. Lithium's in period 2, sodium's in period 3. Sodium's much larger simply because with every step down the periodic table you add an energy level. And so every energy level makes the atom quite a bit larger. And so that's the simple reason for the atom getting larger going from top to bottom. Alrighty, I want to talk for just a minute about ionic radii. As I've said before, you assume all elements in the periodic table are neutral unless you're talking about a chemical reaction or a compound, existing compound. But we will be going into chemical reactions real soon. So I want you to think about or be aware of the radii of ions also. So just kind of as an initial reminder, let's look at lithium, for example. I'm not sure if you remember, but metals, which are located to the left of the stair step on the periodic table, tend to lose electrons to become cations, right? And nonmetals, which aren't shown on this slide, but they're to the right of the stair step, tend to gain electrons and become anions. So what happens to the size of an atom when it becomes a charged particle, an ion. It depends whether it's becoming a cation or an anion. So again, metals tend to lose electrons to become cations, and they always get smaller, okay, always. So a cation is always smaller than the neutral atom it comes from. So this is just putting into words what I just said. Metals tend to lose valence electrons to form cations. And the cation, the size of a cation is always smaller than the size of the neutral atom it comes from. Nonmetals, those to the right of the stair step, tend to gain electrons and become anions or negatively charged ions. And because of the increased electron-electron repulsion, you've just added another negatively charged electron, the anion radius actually gets a little bit larger than the neutral atom. So what is the overall trend of cations and anions as you go down a group and across a period? Well, as you go down a group, atomic radius or size of the ion increases just as you would expect. Okay, you still have the added energy levels. Now, it's a little bit odd and much more complicated explaining the periodic trend for radius or size as you go left to right across a period. Because half the elements in the period are going to be metals and they're going to become cations, and the other half, once you reach the right side of the periodic table, are nonmetals that are going to become anions. Okay, so let's look at each type of ion separately. This picture will help explain what I'm trying to say better. So as you go left to right across the period in the periodic table, looking at the common ions for all the elements, you can see that, as I said, looking just at the cations, for example, the atomic size, atomic radius decreases going from left to right. However, once you pass the metals to the left of the stair step and you start getting into the nonmetals, remember now that nonmetals tend to gain extra electrons when they become an ion to become anions, okay? And so when you add an extra electron, you increase electron-electron repulsion. So this, the nitrogen anion is larger than if you were to look at neutral nitrogen. Okay, whoops, neutral nitrogen would be smaller. I drew that about the same. So anions in general are larger than the neutral atom they come from. However, looking at the trend of anions, so starting to look at nitrogen, then oxygen, then fluoride anions, you can see that going from left to right, they also decrease in size, just as cations do and just as neutral atoms do, for the same reason. Because with each step to the right, you're adding another proton into the nucleus, which increases the attraction of the nucleus for the outer electrons. And because that attraction is stronger, these outer electrons pull in toward the nucleus, making the whole atom smaller. Now, cations and anions, as well as neutral atoms, as you go from top to bottom down a group, get larger, all for the same reason, because with every step down the group, you're adding another energy level of electrons. What I suggest to do here is to test to see whether or not you have understood what I've gone through. And so I would cover up this section of the slide and I'd turn off the video and see if you can correctly answer these questions. It's simply asking you which of the two is larger. And then after you try it on your own, turn it back on and I will explain. All right, let's look at A, and that's comparing nitrogen and fluorine. So the first thing you're going to have to do is locate them on the periodic table. Then you're going to have to remember the trend. What happens to size going left to right in a period? It decreases. So the larger one is actually going to be nitrogen. The second one, we're comparing carbon to germanium. They are now in the same family or group 4A. So the trend for a group going from top to bottom is the size increases because you're adding energy levels. So in this case, the germanium should be larger. Okay, the third one is comparing aluminum to nitrogen. All right, so you've got to consider both trends here. You've got to consider the trend involved in going from left to right because aluminum is farther left. And you also have to consider the trend going from top to bottom. Now, if the trends go in the same direction, like they both make it larger, they both make it smaller, that's great. If they go in opposite directions, one makes it smaller, one makes it larger, it can be tricky. So let's look at that. Going left to right, the size gets smaller. Okay. Going from top to bottom, the size gets larger. Okay. So both of these encourage that suggest that nitrogen should be the smaller of the two. Okay. It's smaller than aluminum because it's to the right of the periodic table, and it's smaller than aluminum because it is farther up on the periodic table. So nitrogen is the answer there. Let's see. Here's another one where you have to consider the both trends going across and down. So germanium, going left to right, germanium's farther to the right, which if you look at that trend alone, would say that germanium might be smaller, right? It's to the right. But then as soon as you look at the trend going from top to bottom, you're like, whoops, germanium's farther down the periodic table, which suggests it should be larger because it has more electron energy levels. So I won't give you this type on the test because you really need a table of data to know for sure. Probably in most cases, the up and down movement is more significant. Adding an extra energy level is more important. So my prediction without double checking would be that germanium would be larger. But again, you won't see one like that on your test. All right, so moving on to another property that exhibits periodic trends. We've just talked about size. We're going to talk about ionization energy. That's in my opinion, that's the most important one. So first of all, what is ionization energy? It is the energy required to remove an electron from an atom. And so that's important for a lot of chemical reactions. What is the trend for ionization energy? Okay, so as you look at a periodic table, as you go down, top to bottom, down a column, ionization energy decreases. That means the energy required to remove an electron is lower at the bottom of the periodic table and higher at the top. It takes more energy to remove an electron from a smaller atom, and that is because the electrons in a smaller atom are closer to the nucleus, therefore more strongly attracted to it, more tightly held, and it takes more energy to yank them out. Then going left to right across a period, the ionization energy increases. In other words, it takes more energy to remove an electron from an atom on the right-hand side. Okay, so the upper right-hand corner is the highest ionization energy of the entire periodic table. The electrons are closest to the nucleus. They're held most tightly because there are more protons on the right side, and so the ionization energy is the highest. So it's just kind of a 3D look at the trend for ionization energy. So in general, you can see that it gets easier. Lower energy is required as you go down a group. And in general, you can see that the energy required to remove an electron increases or goes up from left to right. However, what I want to point out here is there are some anomalies. So let's look at period 2. It's the ionization energy to remove an electron from beryllium is higher than the ionization energy to remove one from lithium. As I said, ionization energy going left to right should increase. But check this out. Boron goes down a little bit and then goes up again, and then it goes up again, and then whoops, it goes down to oxygen. So there are a couple of anomalies in each period with reference to ionization energy. All right, so I'm going to go ahead and try to explain these exceptions to the trends. Why is it easier to remove an electron from boron than it is from beryllium? Okay, boron has another proton. They should be held more tightly. But there's something magical about boron that's making it easier to remove an electron. There is another anomaly between nitrogen and oxygen. So you would expect oxygen to have a little bit higher ionization energy than nitrogen if it's following the general trend, but it's actually lower. So let's look at the orbital configurations for nitrogen and oxygen and see if we can figure out why is it so easy to remove an electron from oxygen. All right, so here are the orbital configurations for nitrogen and oxygen, neutral, okay? So what does ionization energy mean? What is it? It's the energy required to remove an electron. So let's look at the electron we'll be removing from nitrogen and oxygen if we make them an ion, and see what it does to them. All right, so if we remove the outermost electron from nitrogen, we end up with an orbital configuration like this. If we remove one electron from nitrogen, we end up with an electron configuration like this. So you can see, hopefully you remember, that there's something very stable about sublevels that are either half full or completely full. So look what happens. It's very, oxygen has an unusually low ionization energy, which means it's unexpectedly easy to remove its electron. Why is that? Because when we remove an electron from oxygen, we have moved to a half-full p sublevel, which is very stable. So that explains that anomaly. With the trends in mind, the general trends in mind, let's see if we can work out a few sample problems. So as before, I would suggest turning off the video, ignoring the answer key for now, and seeing if you can answer these yourself. Each one is which one of these pair has a higher ionization energy. So it's saying which one requires more energy to remove its electron. All right. For A, comparing aluminum and sulfur, they are on the same period. So you have to remember the trend for ionization energy. As you go left to right, ionization energy increases, which means that sulfur should have a higher ionization energy than aluminum. And in the second one, arsenic and antimony are in the same group. And so the trend for ionization energy going from top to bottom is ionization energy decreases. It gets easier to remove an electron the farther down in the periodic table because the electrons are in energy levels that are farther away from the nucleus and more loosely held. Alrighty, so as with all trends, if the elements are on a diagonal and the effects are competing with each other, it's difficult to tell. So let's look at these. The trend going left to right is that ionization energy increases, and the trend going from top to bottom is that ionization energy decreases, okay? But the nice thing about that is both of these trends suggest that the ionization energy for nitrogen should be higher. It should be higher because it's farther to the right. It should also be higher because it's farther up. So those favor that nitrogen is in fact has a higher ionization energy. The next two are going to have competing trends. So the left to right trend suggests that chlorine should have a higher ionization energy, okay? But the top to bottom trend suggests that chlorine should have a lower ionization energy. So you really don't know which one of those. You can make a guess, but again, I won't give you an uncertain question like this. Alrighty, one more thing about ionization energy before we move on. The ionization energies we've talked about so far are called first ionization energy, and it's removing the outermost electron. But if you supply an atom with enough energy, you can remove, the 2 electrons, 3 electrons, 4 electrons, okay? So sometimes you'll see a comment about second ionization energy, third ionization energy, and there's one important reason that scientists will do that. It turns out that the valence electrons are much easier to remove from an atom than the inner core. No surprise, right? The farther away, more loosely held, okay? So it's pretty easy to, for example, let's look at nitrogen. Okay, nitrogen is in group 5A. It has 5 valence electrons. So it's pretty easy to pick off all of the valence electrons, the electrons in the second energy shell. It turns out once you remove all the valence electrons, the ionization energy for the next one, which is a core electron, goes through the roof. It becomes extremely high. So if you have a substance and you don't know what it is, and you do successive ionization energies, the ionization energy that gets all of a sudden really, really high means you reach the core electrons. So you can find out how many valence electrons a test sample has. So let's look at that in chart form. These are the elements in period 3. And so as we know, sodium has 1 valence electrons in group 1A, magnesium is in group 2A, aluminum in 3A, silicon in 4A, etc. Okay, so in case you have forgotten, the number of valence electrons equals the A group numbering. All right, so sodium has 1 valence electron. Okay, so the first ionization energy to remove that electron, 496 kilojoules per mole. Look what happens when you try to remove the second electron in sodium. Now you're down the core electrons because there's only 1 valence in sodium. It increases by about a factor of 10. That's huge, as you'll see. Look at magnesium in group 2A. It has 2 valence, okay? So about 700 kilojoules per mole, and roughly doubles to 1,500 kilojoules per mole, which you would expect. It gets harder and harder to remove progressive electrons. But then, all of a sudden, trying to remove the third electron, which is not a valence electron anymore, remember? Magnesium only has 2 valence electrons. So now this is a core electron, and it is about 6 times harder, not 2 times harder. So there's a big jump. So if you're given a mystery element, so let's just look at sulfur. Let's pretend you didn't know that was sulfur, and I just gave you these ionization values and said how many valence electrons does this substance have. You would look for trends in the ionization energy, okay? Let's see, about doubles, not quite doubles, not quite doubles. Yeah, that doesn't quite double still. Yeah, it doesn't quite double still. Whoa, okay, that's almost a factor of 3 larger. That is a big jump, okay? So that means that you would, all these ones that were easier to remove, you would call valence electrons and just count them. 1, 2, 3, 4, 5, 6. So this substance, you would say, has 6 valence electrons, okay? All right, the last periodic trend that we're going to talk about in any detail, is electron affinity. And it's the energy it's typically energy that's released when you add an electron. So ionization energy is the energy required to remove it. Electron affinity is the energy associated, and again, it's typically energy released when you add an electron. So here's just kind of a reaction to show you that. Alrighty, so trends for electron affinity. As you go left to right across a period, electron affinity increases. Okay, so when we say it increases, it's becoming more negative. So it's really technically decreasing, but because most electron affinities are negative, see, it means that most of them are exothermic. It's favorable for most atoms to get another electron. So we don't really pay attention to the negative sign when we say it's increasing or not. So that's an important note to make. So we would say the electron affinity of fluorine is the highest on the entire periodic table. Okay. And what we mean by that's the most negative. Okay. The highest energy change. I see that this bottom bullet is kind of hidden. So let me point it out to you. There's not a clear-cut trend for electron affinity going from top to bottom. I think the noble gases decrease, but it's not something I'm going to expect you to know. It's pretty erratic going from top to bottom down a group. So just make sure that you know that electron affinity increases left to right across the period. So, alrighty. This isn't much detail. I guess I lied a little bit. We're going to talk about metallic character. That's pretty obvious, I guess, right? Because if you drew a periodic table and had the stair step, whoops, that was bad. The metals are to the left of the stair step and the non-metals are to the right. So it's pretty clear that metallic character increases pointing toward the metals, going from right to left increases, right? But what is the trend going from top to bottom for metallic character? It actually increases going down. Okay, and a way to remember that is if you look over like on group 4, the top of group 4 you've got like carbon and silicon, and those are considered nonmetals. And at the bottom you have like lead and tin, those are metals. So metallic character gets stronger at the bottom of the periodic table. Alrighty, here is a summary slide of all of the trends. It's, I think, a really handy diagram, and it's one that I might ask you to create on your test. So please do so. It's a good review. Ionization energy increases left to right and increases bottom to top. So the element with the highest ionization energy is in the upper right. Electron affinity. So that has highest ionization energy and electron affinity. So I think it'll help you to realize that the trends for electron affinity and ionization energy mimic each other. All right, the radius goes in the opposite direction, okay? It decreases going right to left. Increases going right to left. So you have larger atoms and ions to the left, okay? And it also increases going top to the bottom. So the largest atom or ion on the in the periodic table is on the lowest left. And the smallest on the periodic table would be helium. So that'd be a smallest radius. Okay. And then metallic character. I put these diagonals. I want to explain them because some people prefer them, but let me show you this way first. So metallic character increases right to left, right, as you point toward the metals. Okay. And metallic character also increases top to bottom. All right. So what these diagonal things show you, you can either show the individual trends with an arrow on the horizontal and vertical direction, or alternatively, okay, you can draw a diagonal, which tells you the same thing, okay? So the direction the diagonal arrow points is towards the element with the largest value of the property you're talking about, okay? So talking about metallic character, this element down here, cesium, I think, is the most metallic on the periodic table, and helium would be the least metallic. And here's a summary of the periodic trends in table format if you prefer that. So again, we have gone over atomic radii trends, ionization energy trends, electron affinity, and metallic character. That's it and for this lecture as well as chapter 3.